Okay, and today's lab, this week and next week's dry labs are all you need are proper shoes. You don't have to worry about lab coats or goggles. Okay, now let's go over to OneNote. Okay, so let's jump into this molecular line drawings. Okay, organic chemists and biochemists. I've mentioned this before at the end of the lecture on last week. If we look at a formula like C3H8, organic chemists don't display the structure like this. And this is a review, this is a repeat, but I just want to make sure everyone's on the same page here. Organic chemists, except for day one, first 15 minutes of class, the STEM organic class, which is a whole year course, they will spend that much time with this kind of a structure. They'll immediately go to the line structure. Now, the line structure is a very shorthand way of representing that this is propane, that structure. So what they do is we have lines, and the lines represent carbon atoms at the beginning of the line, 1, 2, 3, and at the end. And every time there's a kink in the line, that's also a carbon. So that's what that line represents. Now, it assumes that you know that carbon via the Lewis dot structure has 3 singleton electrons. Because it has, 4 singleton electrons, each electron can pair with another singleton electron. Like, go ahead. Was someone going to say something? So 4 bonds. That means this carbon here has 3 hydrogens around it. Hydrogens are not shown on line drawings. This carbon on the other side has 3 hydrogens around it. The carbon in the middle has 2 hydrogens. Now, if you see a biochemical structure of glucose, for example, this is the way it's drawn. So each time there's a kink in that line, there is a carbon there. So this is the formula for glucose. So there are 12 hydrogens around that glucose molecule. Now notice the H's are displayed when the H's are connected to a non-carbon. So in this case, over here, the H is connected to an oxygen, not a carbon. Down here, for example, that carbon there has 1 carbon coming off of it, an oxygen coming off of it, another oxygen. That's 3 bonds. That means that carbon has to have another bond. And that other bond is an H, which is not shown. And you got to get used to knowing where to put the H's and the implied H's. Okay, so no hydrogens off of carbon are displayed. So the H's are displayed on non-carbons. For example, if we had an amine, amines have nitrogens, okay? So if we had this amine, 2 carbons, 2 carbons, nitrogen here. The line drawing for that would be, okay, the hydrogens on the carbons don't show. So we start here and go 1. Okay, that represents 2 carbons, beginning and end, no kinks. Okay, then we have a nitrogen coming off of there. That would be what that would look like. Let's look at an alcohol. Alcohol has an OH group on it. So let's look at this alcohol. Okay, that's ethanol. I'm going to be talking a lot about alcohols in Unit 1. Okay, the line drawing for that would be start at the beginning, because it has 2 carbons, ending, carbon, carbon. And then we're going to have the OH coming off of that carbon. Organic acid. You can look at acetic acid. Line drawing for it would be say we had an ether. An ether is got a carbon, oxygen, carbon bond. Similar to an alcohol, only instead of being about hydrogen, it's got a carbon attached to it. So let's look at that. Okay. The line drawing for that's going to be have 1 carbon attached to the oxygen in the middle. That's what that would look like. And always good to put your pairs in there. Now this takes some practice. Going from a line drawing like this to the formula. To this drawing with all the hydrogens in it to the line drawing. You need to be able to go back and forth with these two. But in your mind, you have to visualize this one. Okay. Are there any questions so far? Yes, I will print that one off. The question is, can I please print the first slab? Yeah, it's not fair to now you don't have to have a printed version of it. You can also just go from your phone, but I will print them off anyway. Okay, so let's. Okay, so basically with line drawings, you've got, they're almost like a schematic of the skeletal carbon backbone. So hydrogens aren't displayed and the C's are not displayed. So carbons are at the beginning. And any kinks. So like going back over to here, beginning, end, kink, 3 carbons. Glucose, we've got carbon, 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 that's 6 carbons. We've got 6 oxygens, so we have 1, 2, 3, 4, 5, 6 oxygens.
Professor, I don't think we're able to see what you're doing.
I was trying to make dots. Let's see, let me do it in another color. Let's see, okay, let's go back to glucose again. Do it in yellow, okay? So we've got, it says 6 carbons there. So we're having 1 carbon, 2, 3, 4, 5, 6. Okay. 6 oxygens. So we have 1, 2, 3, 4, 5, 6 oxygens. 12 hydrogens. Okay, so we've got now the hydrogens that are showing, except for this one here, the hydrogens that are showing are only attached to non-carbon atoms, in this case, oxygens. So how many hydrogens do we have attached to non-carbon oxygens or non-carbon atoms? Here we have 1, 2, 3, 4, 5 of the 12. That means the other hydrogens are hanging off of this carbon, this carbon, this carbon, this carbon, this carbon, and this carbon. So there's 1 here, 1 here, 1 here, 1 here, 1 here, 2 here. So that's 6 hydrogens there. If we count the rest of them, we'll end up at 12. Biochemists never, they'll have formulas like this, but they won't show any of the hydrogens when they actually draw the structures. Now we're going to be drawing a lot of structures in this class. A lot. Unit 2 is on aldehydes and ketones, which is the chemistry of carbohydrates. Okay. All right, so let's practice this some more. Are there any questions about what we've done so far? Okay, so let's look at if you look at the cover of your lab packet. So I'm pulling up the lab packet right now here. Hold on a second. Okay, that's the first page in your lab packet. Okay, so let's look at this molecule. It's got nitrogens in it. It's got oxygens in it. This is called caffeine. This is what caffeine looks like. And frequently with lab manuals, they'll have the structure of caffeine, since caffeine is an important aspect of student life. Okay. Let's see there. Okay. Yes, there is a notation for double and triple bonds. Actually, the caffeine I just showed you had double bonds in it. The reason why we don't acknowledge the hydrogens on carbon is because there's a zillion of them, and biochemists are, in general, don't want to write out all the H's. It's that simple. Same with organic chemists. The main thing they want is to get the backbone structure of the carbon. And then any hydrogens that are attached to non-carbon atoms are shown. That'll make a difference in the chemistry of the thing. But hydrogens attached to carbon backbones don't do any chemistry. They do a little bit on oxidation and reduction, but not a lot else. And then the carbon backbones in organic chemistry and biochemistry are the basis of everything. So what they do is they just say, well, we're just going to assume that there's a line on there, and that's attached to carbons and hydrogens. And then anything else they have to put on there. Okay, so let's go ahead and do some more practice with this. Okay. Okay, so there was a question regarding double and triple bonds. Now we're not going to be doing triple bonds because there are no triple bonded carbons in our bodies, and this is an allied health strand. But carbons will have the capability to triple bond. So do nitrogens. Okay, so if we look at this chemical here, okay, so it's a 2-carbon backbone, so that means it's going to be beginning and end with no kinks, and it's double bonded, so it's going to look like that. So there's a carbon there, carbon there. This is what it looks like with no carbons. Okay, if we had So that would be C4. We have 2, 4, 6 hydrogens. Now notice, again, carbon has 4 bonds. 2 of the bonds are in the double bonds, so that's 2, 3, 4. For carbon number 2, it's 1, 2, 3, 4. All the carbons here have 4 bonds, 2 of which are a double bond. And likewise, if we had a triple bond, 3 of the 4 would be in the triple bond. Okay, so what would the line drawing look like for this thing? Okay, so we have 4 backbones. We have to have a line drawing representing 4 carbons. So 1, 2, 3, 4. The first 2 have a double bond, and the last 2 have a double bond. That would be the line drawing for that. How about if we had something like that? Okay, so it's 3 carbon backbone. 1, 2, 3. The last carbon has got an OH attached. And the first 2 carbons have a double bond. This is what isopropanol looks like, or rubbing alcohol. Okay, again, 3 carbon backbone. 1, 2, 3. The OH is attached to the middle carbon right here. And then we just have single bonded carbons and hydrogens attached. So that's what isopropyl. Or no. That's an A. All right, is this starting to click? Better? Yeah, the root name, we haven't gone into alkenes yet. That's our next chapter. And we'll talk about how to name alkenes. So don't worry about that. Yes, the name will have the basis of where the double bond is, also the location. Okay, let's see here. All right. Let's practice this a little bit more. Now, this also applies to cyclic compounds like you saw on the caffeine. Say we had a thing like that. So, okay, so we have a cyclic compound, and this is called a heterocyclic because it's not all carbons, it's got an oxygen in there. So what would the line drawing look like for that? Okay, we have the 4 carbons are represented with those. And then we have oxygen. There. So that's what that would look like. So again, we have carbon, 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 carbon. And this is called an ether, by the way. Carbon, oxygen, carbon. That'll be our third chapter we're going to be talking about is alcohols and ethers. Okay, I'm presuming you are reading the chapters that are consistent with the lectures. Chapter 12 on alkanes. The book is pretty good. It's very consistent with what I lecture on. Also, I included the slides for chapters 13 on Canvas. Someone asked for the slide PDF last week. Okay, so do you want some more practice with these line drawings, or do you want me to go ahead and go on? And these are just a matter of practice, that's all. Just doing a lot of them.
Can we have more practice, please?
Okay. Let's go the other way. Let's write the formula for this guy here. What's the formula for that? First thing you do is count the backbone carbons. Okay, so we have 1, 2, 3, 4. Are there any non-carbon atoms besides hydrogen? No. Well, how many hydrogens do we have? Well, we have, remember, again, carbon has 4 bonds. So that's 1, 2, 3, 4. So that's 3 hydrogens. Hydrogen, 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 hydrogen. So that's 3, 5, 6, 8. Let's do now make sure when you draw, notice when I drew this OH here, I could have drawn it this way. I could have drawn it this way. Or that way. So whenever you put one of these on, don't just extend the line. Either do it like that or like that. And not like that. You want to make sure you have a kink in there to represent that carbon. This has no kink over here. So you don't know there's a carbon there. Okay? All right. So let's get the formula for that guy there. Okay, we've got 1, 2, 3, 4, 5 carbon backbone. We've got a OH in there. So it means there's 1 oxygen. So how many hydrogens do we have? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, I'm not hearing any questions. Let's see what the chat looks like here.
Can I ask you, how do you identify exactly how many hydrogens attaches to each of the carbon points on the drawing?
Okay. You're right. I forgot about the hydrogen on the oxygen. So this is really. Yeah. Yeah. So, Juliana, that's right. Good. Okay, so figuring out how many hydrogens. Okay, carbon needs 4 bonds. Typically, with single bonded carbons like this here, you need 4 bonds for this N carbon right here. Well, one of the bonds, one of the 4 is attached to another carbon. So the remaining ones are hydrogens. That means that's 3 left over. If this carbon here has 2 carbon-carbon bonds of the 4, so that leaves 2 left over. So those are 2 hydrogens. This one here, we have a carbon-carbon single bond and a carbon-carbon double bond. So that's 3 bonds total. So that leaves 1 hydrogen. Same over here, this carbon here. Then on the end here, we have a carbon-carbon double bond, excuse me, a carbon-carbon single bond, a carbon-oxygen single bond. That's 2 of the 4, so that leaves 2 hydrogens left over. Okay?
Thank you.
Sure. Trying to keep up with the chats here. Okay. It's kind of like bookkeeping with carbon. Carbon needs 4 bonds. So what's attached to it? So that you can get those uh, number of hydrogens and other things attached. Okay, so let's see. Let's do one more. I'm going to end lecture a little early today because I'm going to photocopy those new dry labs for the day. Let's do okay, let's look at this guy. Cyclic, heterocyclic. Hetero again means that it's cyclic and cyclic with other, in fact, let's change it slightly. Put a nitrogen instead. We have a lot of nitrogens in our body. So nitrogen is a very important element in our body. Okay, so let's come up with a formula for that. Okay, the backbone, the carbon backbone is 4 carbons. 1, 2, 3, 4. We have a nitrogen. Now, nitrogen, if you remember from your Lewis dot structures, has 3 bonds. So nitrogen, 3 bonds. Okay, so this nitrogen here has got, on its 3rd bond, is a hydrogen. Okay, so this carbon here has got a single bond to the nitrogen and a double bond to the carbon, leaving one hydrogen left. This is a double bonded, this carbon here has got a double bond and a single bond, leaving one hydrogen. Same here. Same here. Again, we're looking at, let's complete this here. So it's going to be 5 hydrogens. If we had the same structure, oxygen needs 2 bonds. It's already got 2 bonds, so there's no hydrogens attached there. And we've got a hydrogen here, hydrogen here, hydrogen here, hydrogen here. So it would be C4OH4.
Professor, quick question.
Yeah.
How many bonds does oxygen need?
2.
Just 2. Okay, that's what I thought. Okay, perfect. Thank you.
That's why there's no hydrogens on the oxygen there.
Right. Okay, thank you.
And then and correspondingly, that's why the nitrogen has the hydrogen on it, because it needs 3 bonds. It has to do with 2 singletons, 3 singletons, 4 singletons in the Lewis structures. The single, then I guess I should spell it out. Okay, okay, so let's look at this one. Okay, we have a 3 carbon backbone. We have 2 oxygens. And this is a carbon-carbon single, so we have 3 hydrogens there. This is 2, this carbon here, it's got 2 single bonds to other carbons, so that leaves 2 left over. And this carbon here has 1, 2, 3, 4 bonds already. So no hydrogens are on that carbon. And then we have a hydrogen out here on the other side of that oxygen. So we have 3, 5, 6. This is a propanoic acid. Okay, a good worksheet for doing this is actually part of your tri-lab that you're not doing. And what I'll do is I will pull out the parts and make it into a worksheet just on this. Okay, I'd like to go on into alkenes right now. At least start the unit on alkenes. Are there any more questions about line drawings? Okay, so let's now We're going to jump into chapter 13. Okay, so chapter 13 talks a little bit about polymers. We're going to be talking about organic polymers, not synthetic polymers. And also, we're not talking about alkynes, which are triple bonds, because there are none in our body, in organic systems in general. Okay, so notice that this says unsaturated. Chapter 12 was on saturated. Unsaturated means double and triple bonds. And you hear saturated and unsaturated a lot when you talk about fats from a nutritional standpoint. Single bonded fats are typically coming from animals, beef, pork, lamb. You get a lot of not triple bonds, but double bonds from fish and vegetables in terms of the fats. They also have something called polyunsaturated. That means more that's more than one bond. Polyunsaturated fats, for example, frequently are found in vegetable oil. Excuse me. The good news on polyunsaturated fats, they are known to cause less detrimental health effects. However, one of the cons on polyunsaturated fats is they oxidize easily. In fact, if you have a bottle of vegetable oil you're cooking with, when you get towards the bottom, you'll notice that around the top, it starts getting a little sticky. And that's because the oil has oxidized and has polymerized. That's why it's sticky. And that is very unhealthy, polymerized oil. Excuse me. Okay, so alkenes the double bond. Not worrying about alkynes, the triple bond. And there's something called aromatics. Now, there's aromatics in cooking. They'll frequently refer to like onions and garlic and stuff. They'll say, oh, the aromatics. In organic chemistry, when we say aromatics, we're specifically talking about benzene rings or fused benzene rings. All right. Yes, last lecture we talked about naming of the alkanes, and we talked about like dimethyl. In terms of alphabetizing, the di doesn't count. It's the M or diethyl. It's an E. We're going to be talking about isopropyl, for example, or isobutyl. The iso is part of the actual structure, so it counts as an I. That's what they're talking about here. Okay. So let's talk about naming. Again, it follows the same rules. Okay, we've got 3 parts. This is branch. Backbone. And functional group. So let's look at this here and let's ignore this for a second here. Okay, so we look at this. It's got 1, 2, 3, 4. By the way, the line structure from this is going to be like this. The line structure for this is going to be okay. So the backbone. On this one here, there are no branches. When we do the backbone, we are going to do that. And no branches, so we don't have to worry about. Remember, branching is if there are no branches, you don't have to include that part. Backbone on this first one is 4 carbons. So 4 carbon backbone. And that would be a buta. Okay, now we're going to have functional groups from now on for this last part. In chapter 12, the functional group really wasn't there because it was an alkane. Alkanes, a functional group was an H, which is kind of weird to say it's a functional group. However, this one, there's a functional group. And the functional group is a double bonded carbon. So, and that is an ene. So this is a butene. Now, whenever we have a functional group, we have to say what carbon, just like with branches, we have to say what carbon the functional group is located on. In the case of a double bond, there are 2 carbons that anchor the double bond. Now, depending on which way we number this, we number from left to right like this is. The first carbon that encounters a double bond is carbon number 2, and it goes to carbon number 3. So over here, it's going to be 2-butane. As a first encounter of the double bond, it's on carbon number 2. 3 doesn't come into play. It's like the direction we're numbering. In this case, the direction is this way. So the first one we encounter is carbon number 2. This one here, the functional group, if we start from the right going to the left, the functional group is on lower numbered carbon, so we number from right to left. So here we're going this way. So the first carbon is going to be on carbon number 2. So let's name this one. Okay, 6 backbone, and there's no branching. So that's X. And the functional group is in double bond, so it's an ene, so that's hexene. And the first carbon is carbon number 2, so that's 2-hexene. Okay, so let's look at one with some branching. Okay, so we have now, whenever you do a backbone with a functional group, the backbone has to include the functional group. So for example, we couldn't have a back, we could not have a backbone like that, even if it was longer than the other one, because it doesn't include the functional group. So we can go like this. Or like that. So let's go with the yellow. Okay, so that's 4 carbon backbone. Oops. Or we're back to the buta, and it's a double bond, so that's an E. It's butane, and we're numbering from starting here going this way. So that's carbon number 1, so it's 1 butene. And we have a branch there. So that would be 1 methyl. 1 butene. Oh, excuse me, not 1, 1, 2, 3. Three methyl 1 butene. Now, the backbone with the functional group determines numbering. As soon as we determine that, it's permanent, the numbering, the carbons. And when we add the name for a methyl group there, that does not, we have to stick to the original naming with the functional group. It's not 2-methyl. It has to be numbered that determined the carbon naming. Okay, so that's 3-methyl 1 butene. First thing we're going to do is going to determine the backbone. Okay, so that's 6 carbons long. And it's got a double bond in that. That's the functional group. So it's a hexene. And using the numbering system they have already down there, it's going to be 2 hexene. And the branch is on carbon number 4. So it's 4-methyl 2 hexene. Now, we can have multiple functional groups. Like in this case here, in this case on the left, we have 2 double bonds. On the right, we've got a cyclic alkene with 2 double bonds. So these we run into in our class less frequently. We'll frequently see a single double bond. Sometimes we'll see 2 double bonds. If we do have 2 double bonds, this would be the way we name it. Again, 3 parts. And we've got, what's the backbone here? It is this guy here. Remember, it's got to contain the functional groups, the double bond. So this is going to be an ene. And it's going to be a butene. But there are 2 double bonds. Let's say diene at 1, 3. We have a couple branches. So it's going to be 2, 3, dimethyl 1,3-butadiene. Now that's probably the most complicated we've done so far. Okay, so let's practice a little bit more on this. Let's do, let's start with a line draw. Okay, let's name that. Okay. And let's throw in a branch through there. Okay, so again, the backbone has got to contain the functional group. In this case, is a double bond. So we're gonna go boom, 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 and we have a chance to go up or to the right. And going up is one carbon, to the right is one carbon, so it doesn't really matter. So let's just do that. And then we have a branch here. Okay, so we have 1, 2, 3, 4, 5. So it's got a double bond, so it's pentene. And what carbon number does it start on? Now, carbon number 2, so it's 2-pentene. And the branch is on carbon number 4, so it's 4-methyl 2-pentene. Yes, there's a write-up for the dry labs. Oh, I mean like a pre-lab write-up? Who asked the question? Caitlin. There's no pre-lab for dry labs. Is that, if that's what you mean? And I guess Tim asked the question about the lab write-up. Yeah, it's a series of questions. It's kind of a worksheet to work through, focusing on chapter 12. Okay, how do you know what's the backbone? Okay, the backbone contains the functional group. In this case, the functional group is a double bonded carbon right here. So the backbone can go one of two ways. It can go this way, or it can go this way. They're the same length. So let's just choose the yellow one. That means that's going to be a branch. So how long is our carbon? 1, 2, 3, 4. So it's going to be a, oops. When it's a double bond, so it's going to be an ene. 4 carbon long, that's a butene. Okay, so on carbon number 1, we have a branch at carbon number 2. And that is 2 carbons long, so that's ethyl. So 2 ethyl, 1 butene will be that one. Your chat says, Caitlin, where do you get the root? Ah, it says, why wouldn't it be a pentene? Okay, pentenes contain 5 carbons. The backbone contains 4 carbons. That's why it's a butene. So this is 4 carbons. Okay. Now this backbone numbering, the top to the bottom. That would not include the double bond. It says, why can't you go from top to bottom? You mean like that? Yeah, exactly. Because it doesn't include the double bond. Exactly. Okay. So again, his question was really important. And I kept emphasizing it. The backbone has to contain the functional group. Period. No exceptions. Now it gets tricky when you have 2 functional groups on the backbone. And we're not going to cover that a whole lot in here, but there will be a few times when we get into fats, for example, where we have a double bond and we have an organic acid. That's functional groups. But it'll be more of the exception than the norm. Okay. All right. Now, remember from Wednesday, I said single carbon bonds can rotate freely unless they're in a cyclic configuration. Then they become rigid and they cannot freely rotate. Double bonds are the same way. Okay, that double bond is rigid. Hence, that's the backbone. That double bond, now this is a single bond here. So double, single, single, double, single, single. So those can freely rotate, not a problem at all. But not the double bond. So you can get 2 versions of butene. One where the methyl groups are on the same side of the double bond, and one they're across from one another. So we have to designate cis trans. Think of cis as in sister, close together. Trans as in think of trans oceanic, trans, when you travel, you want to go transit. So think of it as far apart. Okay, so whenever, this is a red flag, okay? When you have rigidity, you have cis trans isomers. Okay, so let me give you an example. Okay, so we have okay, so we have a double bonded CC and then single bonds. Okay. Okay, we have rigidity here, right? Because we have a double bond. But do we have cis trans isomers? So if we look at, we put the hydrogens in, we don't have the difference between with the cis and trans, because it would be trans, it would be cis. That's the same thing. So when the double bond is on the end, there are no geometric isomers. Now, like cis and trans fats, they behave biologically different in your body. And the reason for that is they're chemically the same, but their physical properties are different. Enzyme active sites are very, very picky about the way molecules in the active site are arranged. Because they've got all these very, very geometric positioned groups that require the molecule in the active site to be positioned a certain way. If it's designed for a trans molecule and you put a cis molecule in there, the activity in that enzyme will stop working. Or if it doesn't stop working, it'll go very, very down in terms of efficiency. So biochemically, cis trans is very important. Many of you have heard of MSG, right? Monosodium glutamate. Glutamate is an amino acid. It's called glutamic acid. And it comes in two forms, D and L. Now, amino acids, the natural ones are the L form. And our bodies make glutamic acid. They make the L version of glutamic acid. When you buy MSG at the store, you don't get L, you get a mixture of D and L. Some people are sensitive to the D form of glutamic acid. And that's why some people have problems with MSG in their food. But it's because of the geometric isomers between the two forms of our amino acids. So this geometric isomer stuff is real important from organic and particularly a biochemistry perspective. For example, when we get to carbohydrates, we're going to talk about two forms of sugars. There's a D and an L form of sugars as well. For example, glucose. There's D glucose and L glucose. Carbohydrates, the natural form is D, not L. So with amino acids, it's L. With carbohydrates, it's D. So again, very important. As far as physical properties of alkenes, they're basically they act almost the same as alkanes. You know, they're non-soluble in water. They're not particularly polar. Solvents like gasoline, pentane, etc., are very soluble in those, and they float on water, meaning they're less dense than water, and they smell like gasoline. The bigger the molecule, higher the boiling point, higher the melting point. Same with alkanes. You're going to find this trend to be very, very consistent throughout all the functional groups. All right, so reactions. I'm going to stop here. And I want to make sure everyone is comfortable with naming. And I'm going to stop so I have to photocopy that lab for today. Let's do some more practice problems. Are there any questions about naming so far? Now we're going to find that as we go through these chapters, and we'll be having new functional groups. Each functional group has got a ending to it. You know, like with double bonds, we have an ENE. We're going to find with alcohols, it's an OL. We're going to find with aldehydes, it's an AL. Ketones, it's an ONE, etc. So each one's going to have a different name when you're naming. So one thing we didn't practice was going from a formula to a structure. So let's do a few of those. Okay, 5-ethyl. No, it's not going to work. Okay, 5-ethyl 3-octene. Okay, so let's draw the structure for that. Now remember, we have 3 parts again. We have the functional group. We have the backbone that contains the functional group. And then we have branching. Okay, so we have a backbone of 8 carbons. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8. Okay, and it says 3-octene. So 1, 2, 3. That's where the double bond is on the 3rd carbon. That's where it starts. Then we have branching on carbon number 5. 1, 2, 3, 4, 5. And that's an ethyl group. So it's 1 carbon, 2 carbons. So I recommend always starting with the backbone. Find the longest backbone that contains the functional group. That. Then we have one branch. What would the formula for that be? Well, how many carbons do we have? We have 8 on the backbone plus 2 out here on the branch. That's 10 carbons. And we have no other atoms except carbon and hydrogen. So let's count what we have. 3 there, 2 there, 1 here, 1 there, 1 there, 2 there, 2 there, 3 there, 2 there, 3 there. Okay, so that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Let's do another structure from a name. Okay. So we have functional group, backbone, branching. Okay, so the backbone is 5 carbons long. 1, 2, 3, 4, 5. For a double bond, carbon number 2. Okay, and we have a branch, a methyl branch at carbon number 3. That's what that would look like. That would be 5, H. Okay, we have 3 here. 1 there. None here. 2 here. 3 here. So that's 3, 4, 5, 6, 7, 2, 3, 4, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'll get you some more worksheets on doing line drawings. Okay, so any questions about the front end on this chapter 13? Okay,
I have a question.
Yeah.
How is it 12 hydrogens if there's 5 carbons?
I'm sorry, what? Say again.
It says C5H12. How is it 12 and there's 5 carbons?
Okay, so we have a methyl at carbon number 3, right?
Okay.
That's the 3 extras at the end of the methyl group there. Okay, so we have 3 at the beginning. There's 3 there. We have 1 here. We have 3 here. That's the end of the methyl group. That's a carbon right there. And there are none here because the carbon, again, has 4 bonds. We have 1, 2, 3, 4. We have 2 here, 3 here. Clear.
I see. Okay. Thank you.
Does that make sense?
Yeah, thank you.
Okay, cool. Oh, I wanted to show the reactions again. Let's see. Let's go to we're back in Canvas. And yeah, here's the unit 1 reactions. Okay, so we're just getting into alkenes. Now notice with alkenes, we've just added this guy, this reaction, and we can go back and forth between an alkene and an alkane. So now we have 1, 2, 3, 4, 5, 6 reactions. We went from 2 reactions for chapter 12. Now we have 6 reactions. And if you count burning alkenes, 7 reactions. So reactions are a big deal. Now your book goes into a lot of detail on the conditions for the reactions. Now this page right here, you're going to have for your test. You can, I don't want you to memorize it. You'll be using it a lot. And you'll probably end up memorizing it because you're using it a lot, not because you started off by memorizing it. But I'm going to give you this on the test. Okay. So this will be chapter 12 on alkanes. Chapter 13 is alkenes, and we're on now. Okay. Now I need to leave early because I need to photocopy the. Don't bring your lab packet. So Vera, it says, what would be the name of that one? Which one are you talking about? This one here? The name of it would be that. Is that what you wanted? So we have five carbon backbone, double bond, and the double bond is on carbon number 2. Then we have a branch carbon number 3 with a methyl group. So 3-methyl-2-pentene. Yeah. Okay, so I need to print off this worksheet I gave you. The one I didn't, let's see, I forgot whether it's, I need to make sure it's, I saved it on Canvas as well. Okay, so I will meet you in lab at 3. And basically, you can work in groups of 2 or even 3. And this is going to replace lab Dry Lab 1. And this will be focused on chapter 12. Now, next week, don't forget, we have a holiday on Monday, Labor Day. So there's no school whatsoever on Tuesday, on Monday, okay? All right, so I'm going to end this. I'll see you guys in a little while.